record. So last class, I left us off with this thought that we have this odd system where this was preferred to that. And we considered, that's a really awful chair, I'll clean that up. And we considered that the Anchimeric effect should be strong. So I'm going to actually assign a couple of papers. I should send them out tomorrow for the weekend reading for next Tuesday, talking about this. It was a debate between two Canadian scientists, actually, about this, what's going on here, the reverse Anomeric effect. And so the reverse Anomeric effect, the idea there is that positive substituents sit beta. Actually, almost all this Anomeric effect stuff is Canadian. All the arguments about stereoelectronics were done by a professor at the University of Sherbrooke. The discovery of the Anomeric effect was done by a professor at the University of Ottawa, who then moved to Alberta. And then this discussion is between two colleagues at the University of British Columbia. And so sugar chemistry, and especially everything along here, really is very Canadian-centric, which is unusual for chemistry, because most of the time we get left out. Okay. So there's a bunch of arguments for this, over why this could be happening, but there is, I'm not going to say it's complete consensus over why it's happening now, but it's not because of some sort of magical influence or different effect. So any theories as to why the top would be preferred over the bottom?
I know this probably isn't correct, but the first thing that comes to mind is just like sterically, it makes more sense to be equatorial.
Yeah, so sterically it does make more sense to be equatorial. That's a good point. So what we've seen so far is that sterics hasn't been enough, right, to dominate the Anchimeric effect. Correct?
Right, yeah.
Yeah. Okay. So what's different sterically here than if that's neutral? Why? So this prefer over that, but if we take the neutral form, let's just think about this for a second. But that's preferred to that. So I actually completely agree with you, Paul. It is entirely sterics, but it's not fully explained by what we're talking about here. Okay. So when we're doing these kinds of reactions, obviously what we have is we have an oxocarbenium plus some pyridine. So if I draw that, let's say that's the reaction. That's feasible. Nothing wrong. Positive, positive, positive. Bad John. Am I missing anything with how I'm drawing that? Is that explaining everything that's going on? Like, is that everything that's in the flask?
I'm gonna go with no.
I'm going to go
I would.
no too.
I mean, I guess as a solvent.
Right?
Yeah, I don't know.
Okay, so I don't know if you can tell me anything about the solvent. Like what kind of solvent is water the solvent? Why or why not?
Um, I would say that maybe the solvent can't have any proton or like um hydrogens that can be protonated, I guess,
Okay, why would you
since
say that? I agree with you completely.
well the what is it? Is it pyridine? I don't the nitrogen is basic, so I guess it would react with that.
Okay, I'll say that, but I don't think that's the main reason. Let's say we had
Okay.
water as a solvent here. So if you have a solvent, how much solvent do you have relative to everything else in solution?
A lot more.
Yeah, a lot, right? We're gonna get real technical here and say lots. So if you have, is water a nucleophile?
Can be.
Yeah, right. So then what you'd start seeing is you'd start seeing a lot of like OHs attached. But we want that. So this seems like a bad idea to use water as a solvent. And for the same reason, we're probably not going to use ethanol as a solvent. Or like any kind of alcohol. Or anything, as Kirsten was saying there, with a hydrogen attached to a heteroatom, because those are all reactive solvents, because you can remove that hydrogen and then you have a good nucleophile. It's not so much because the pyridine is going to deprotonate it. The pyridine is not a strong enough base to deprotonate water or alcohol. But if you have any of those things, they're going to react with the oxocarbenium because the oxocarbenium is not stable. It's going to react with stuff. So the types of solvents that we can typically use for these kinds of reactions, and we're going to really focus on 3 solvents in this course. It's a bit like 90% of what we're going to do with this sugars are going to involve just 3 solvents, so it's not really that difficult. Ether, acetonitrile, or dichloromethane. But let's, for right now, consider ether. Now, we're also have got to have added some promoters. So let's say there's some silver bromide in here now because we added some silver. We got the oxocarbenium because we added silver. Tired. So there's stuff in here, but there's an awful lot of ether. So when we drew these structures up there, we didn't consider the presence of anything else. We just drew the material and we were looking, okay, what's the conformation of this compound? But unless you're doing reactions in the gas phase, this is not really a description of what's going on. This is just, we're taking a look at this, we're trying to focus on that, but this is solvated. So let's consider how you solvate something like this. Nothing wants to be positively charged. Everything wants to share its charge around as much as it can. So you can imagine that, I'll change color and draw these in different colors. Green. That there's a bunch of solvent molecules that are trying to get close to that positive charge, and they're going to try and donate electron density from the oxygen to that N plus to stabilize it. That makes sense. You'll have the same thing up here. And they're going to try and get close, right? Because you want to get rid of that negative charge or a positive charge. If it was negative, you want to get rid of that too. You want to get rid of charges, whatever the charge is. Okay. So now if we're thinking about this, suddenly there's no steric real, like we know that the sterics don't matter very much for the anomeric, like the anomeric effect can overcome the sterics. But now we suddenly have big differences between these two, because if you look at these guys down here, you don't have a charge. And so the ether molecules can stand off a bit. They don't need to be in as close, they're not going to be as organized. They don't care which way they're pointing. Whereas up here, the ether molecules are much closer in. So suddenly the size of this species isn't the pyridinium. It's not the pyridinium that's giving it size. It's the pyridinium plus all these ether molecules that are trying to get in really, really close. So suddenly this thing's freaking huge. And so why this is happening is because solvent stabilizes charge. Solvent is big. Sterics cause problems. So when we're thinking about this, we need to be careful. And goes with all chemistry. Like it pops up here. This is a really good example of it, where we sometimes focus so much on, and I'm really guilty of this as an organic chemist. I really think about the organic component and what's going on, and I abstract everything else in my mind. But we need to remember to yawn. We need to remember that everything here is happening in the context of the solvation shell, and everything is solvated all the time, and that has a major influence on reactivity. If you change the solvent, you change the reactivity. Like theoretically, if you did these in hexanes, you would not see a reverse anomeric effect. The problem is you can't do them in hexanes because they're not soluble in hexanes, so that never happens. You can't observe it. So in any solvent that it is soluble in, it's soluble in it because the solvent can interact with that positive charge. But because it's interacting with that positive charge, it's making that area bigger. And so it causes this reverse anomeric effect.
If you had like, I don't know why you would do this, but it's more just out of curiosity that I'm asking. So if you had ether mixed with like a nonpolar solvent that like I don't know if does hexane actually mix well with ether? Or...
Yeah, it does.
So in that case, where you have like a mixture of a nonpolar solvent and ether, would you still see the reverse anomeric effect, like predominantly?
Yeah, because the ether, like you'd have a higher localized concentration of ether around here to try and stabilize that charge. So even if you only had 10% ether and 90% hexane, your charge would make sure to grab all the ether it could. But if we use, I think there's actually a paper, I think it's going to be one of the ones I'm sending you, where they actually looked at dimethyl ether versus diethyl ether. Or maybe it was diethyl ether versus diisopropyl ether. And you see a smaller effect. You see a smaller reverse anomeric effect when you use a smaller ether, which makes sense because it takes up less space. Because when you mix two solvents together, it doesn't mean that at any point in space there's there's the same ratio of the solvents. The solvents are going to reorganize based on what's needed to minimize energies around them. Okay. Now, we actually see this thing where what we're going to take a look at now is sort of the anatomy of these reactions and the things we need to think about. So we're just going to stick with this Koenigsegg. And just in case anyone's unfamiliar, R equals something, where we can define it. So what I want to think about is this system, and we're going to talk about a few different effects that can change how solvent works, and I want to make sure I kind of sketch them out here. Actually, I'm going to actually change this to just, I'm going to write promoter up there. Yeah, I think I'm happy with that. So there's a bunch of things that we can change to how, and then let's say there's a given nucleophile, and our nucleophile is, we'll just make our nucleophile ethanol. This isn't the solvent, this is our nucleophile. Not isopropyl, just ethyl. And depending on how we change these conditions, we can change the ratio of the products massively. We can change the yield of the reaction. We can change the efficacy of the reaction. Sorry, OR, still here. So what I want to talk about first is actually the dominant, one of the most important things we need to consider, and I think it's actually the best rule, like it actually follows rules and it actually works every time. And this is a concept called Anchimeric assistance, and I have no idea where this comes from. I don't know why it's called Anchimeric. I should probably look that up. So this is in contrast to Anomeric. They both begin with AN, but they are different things. And this comes from the idea of the C2OH protecting group getting involved. Okay. So I'm going to ask you, because we're going to come back to this later in this lecture, so I'm going to ask you for a moment to grant me the fact that if I have this system, a benzyl group there, a bromide, and I'm using dichloromethane, which is a very neutral solvent, and we're going to come back to why it is. It's not really going to affect the ratio at all. And we're going to do this at about 10 degrees Celsius, which is a moderate temperature. And we're going to use silver, which is going to strip that bromine off basically completely. So I'm just going to note that this is SN1-like. As we discussed last class, is it really SN1 or is it kind of like an extended SN2, and where on that continuum are you? You are on that continuum still, but it's more, the separation is pretty broad. We're really, really opening that bond. And we are making sort of ion pairs and oxocarbeniums. So, and then again, we're going to add our ethanol. We get alpha primarily. And this is due to the anomeric effect. And that's because you make the oxocarbenium, and then your ethanol starts coming in from either the beta phase or the alpha phase, and primarily alpha. Why? Because alpha anomers are more stable. I want to get back to. We're going to come back to this idea. So I think on Tuesday night or Wednesday morning, whenever it was, I uploaded a couple of papers about the Anchimeric effect, and they've got to do with assignment 1, which has also been uploaded. And so you can start working through assignment 1. You can't do all of it, but you can do parts of it. I can make sure you can do. We'll be able to do all of it soon. And a lot of it sort of talks with some of these, I guess, almost philosophical things that we're discussing here. Over what do you think about some of these concepts? How do you think about them? How do you explain them? Anyways, so what we have here is we have what we call a non-participating group. And we're going to see why it's non-participating on the next slide. Because if we contrast that, same conditions, this is exclusively, the other one's mostly alpha, this is exclusively beta. Does anyone want to hazard why? Okay.
Is your alpha face blocked from this
Well, obviously, because it's exclusively beta, but why? I'm gonna go all 5-year-old on you here, and just say why.
When I like vaguely remember learning about the Anchimeric assistance, and when I learned it, it was like the oxygen anchored like the position of the bromine, so then it has to attack on one face of the chair. If
I
that
kind
makes
of
sense.
like what you're saying there. I just want to make sure that we're on the same page.
So it can only attack on a certain side of the.
So you're saying the oxygen anchors. There are 3 oxygens.
Oh, the oxygen of the with the carbonyl.
Right. So what we have here is, let's think about this for a second. We know that charges do not like being localized, right? Charges like being spread out over lots of things. So let's follow that arrow. Because we can make that. But this, of course, is in resonance. With that, and then also with just having the positive charge on the carbon. And we can think of the resonance hybrid as my pen's too thick. Oops. I don't know what I'm doing. I am clearly pressing buttons way too fast. There's a positive charge in the middle. They're spread over the 3 atoms, right? So if we think about it, what's a more stable form, having the positive charge on this oxocarbenium or having it spread out over this acetate? Based on what we know about resonance.
Spread out.
Yeah, right? Because you have it over more atoms. That always wins. Like, nothing special. So if we're thinking about this equilibrium, we're going to lie towards having it with the 5-membered ring. And we know we like making 5-membered rings. Fives and sixes rock, right? Like, we like making 5 and 6-membered rings. And if you try and draw the 5-membered ring with this sort of cis, or sort of with this trans to each other, it can't quite reach. It's very, very awkward. It's possible, but it can't quite reach. You also have a very strong anomeric effect this way. Because again, we just said positive things have really strong anomeric effects, and holy shit do they ever. You have this hydration, like solvation issue thingy happening as well. But the positive charge isn't only on this oxygen, it's kind of spread out, and so this thing is pretty diffuse. So these are really, really stable structures. And so because of this, even if you have these in equilibrium and they're going back and forwards, Susanna's right. You're kind of, and so is Paul, that you're blocking. Just put the positive charge exclusively on that for a second. We're kind of blocking this bottom face altogether. Whether it's directly because we currently have a 5-member ring with a single bond there, or because this is kind of flipping around and almost going to make that 5-member ring and isn't currently doing it, but it's still really close in. It's preventing attack at that face. And so attack comes exclusively from the beta face. And so we can see that thinking about how the ethanol comes in. And this is kind of SN2-like.
Is the bromide forced equatorial, or is this after we've kicked out the bromide?
This is after you kick out the bromide.
Okay.
So you make the oxocarbenium, and then as soon as you make the oxocarbenium is not very stable, and it gets this stabilization from this Anchimeric effect. Because if we want to sort of follow this, we call this A. No, you know what? We should probably call this A. A, B, C, D. Then if we have like an energy diagram, we've got A. B is the oxocarbenium. We got to go up to B. And it's got some transition states, so I shouldn't draw a direct line. I should draw it up like that. Because B is an intermediate. Then C is a lower energy intermediate. Not massively lower, but lower. And then we can follow down to D, which is, I'm going to skip the step where the proton falls off because there's going to be another intermediate, but let's pretend it's thermodynamics. We don't need to draw all the intermediates. It's path independent. We can fall down to D, which is the most stable. But to get to C, we need to go through B from A. Cool. So we're going to summarize all this stuff at the end and all the different things that lead to beta versus alpha, but I just want to talk about why. Okay. So the other big thing that comes in with this Anomeric effect, or this Anchimeric assistance, is relative reactivity. So let's say I have two molecules. I'm going to draw galactose because it takes up less space. I'm lying. I'm going to draw galactose because I love galactose more than any other sugar. I think it's a Stockholm syndrome. I devoted most of my PhD to galactose, and so I think it must be special, because if it isn't, then there's a lot to answer for. So let's say I take that, and I have a 1-to-1 mixture of those guys. I take a silver salt, 10 degrees Celsius, same conditions as what we just did. Stick with dichloromethane. And we have some ethanol. And let's say it's 0.3 equivalents, so not very much. And also only 0.3 equivalents of silver. Okay. Now, we just talked about the product distribution we expect. We expect that the one on the left is going to give us alpha as a major product because of the anomeric effect. So one way we can, I don't know what I just did. I obviously pressed the wrong button, and now it's frozen. Okay. There we go. So one way, if you don't want to draw in all of the substituents because that takes time, one thing we can do is we can just extend that down into the middle of the ring. And what I'm basically saying there is, look, everything on there is benzyl protected. I'm going to just notate that it's galactose by drawing in the one that's different from glucose. Otherwise, we assume it's glucose. So this is a short form annotation we can use to not have to draw in all the freaking substituents. And we just assume that we're working with an audience that knows what we mean with this, which is you guys now. And on this guy, we're going to get beta because of Anchimeric assistance. Okay, so we're only going to get a small amount of this conversion, right? Where we just don't have enough catalyst, we don't have enough reagent. Most of our stuff is going to stay in starting material. Do you think you get more of A or B? Which one do you think you generate more of in this time frame? And actually, you get it's about 3-to-1 is the ratio.
I'm gonna guess that we get more of B.
Okay.
Because I think the Anchimeric effect or assistance is stronger. I'm just guessing. So.
Okay. I'd say it's so. I think this is where we need to be careful with how we're thinking stronger. I'm by stronger. I agree with you that it's a lot more selective. Like the Anchimeric assistance will give us beta. The anomeric effect gives us most of the alpha, but some beta is a little leaky. So the Anchimeric effect is a lot stronger and it's a lot more selective. But that doesn't necessarily tell us which of these is faster. Because saying it's stronger doesn't tell me if it's faster or not. And I'm going to let you off the hook because you actually gave an opinion, so you're free. And it was a useful opinion. Any other opinions with explanations? No opinions. The rest of you are cowards. Okay. Disappointed my graduate students. Okay, so let's just think about what we need to make for this reaction. What's the rate determining step of the reaction? I'll go back because we have it drawn there in the bottom. Susanna.
The rate determining step.
Yeah.
Would it be B?
Yeah, A to B, right?
Yeah.
Because it's the biggest energy difference going forward. That's what that's all rate determining step means, is what is the biggest energy difference. Because that's where you're going to be slowest, because you need to have the most energy to do the dump. So this distance here is the rate determining step because it is the biggest one. And I'm going to pretend I was doing something in French because I got my initials backwards. RDS. So what that is going from, it's basically losing the bromine and going to the oxocarbenium. And that makes sense because we're going up to this really high energy thing. We're going up to a charged thing from a non-charged thing. That's always going to be rate determining. Okay, I'm going to say almost always rate determining, but I can't think of a single example where going from uncharged to uncharged is less energetic than going from an uncharged to a charged. I'm sure there's an example out there that's going to prove me wrong, so I shouldn't say always. But I can't think of any examples where it's not true. Okay. So let's think about what those are. So what's going to drive that, as always, whenever you're thinking about energies of things, it's the energy of the charged species that almost always determines reactivity. Okay, so is there anything we can say about the energy differences between those two positives? And this is before we get the Anchimeric effect coming in, stabilizing the charge, blah, 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 because that happens after the rate determining step, so it doesn't determine how fast the rate determining step happens.
Would the right be more stable because you have a larger charge distribution across the ketone, or?
So let's just draw this out. So, well, we have it up here, kind of. So you're agreeing with Kirsten, basically, that the acetate's faster.
Oh, sorry. I think the anomeric effect is faster.
Okay. I'm going to disagree that it's going to be the anomeric effect that makes it faster, because again, that hasn't come into it yet, because we haven't drawn anything with the product. Something else is happening.
Okay.
Let's just compare that. Drawing these out explicitly. And remember what benzo is. It's hopefully I didn't exchange one acronym that nobody understands for another acronym that nobody understands. If you can't remember what pH is, it is a phenyl ring. I'm sure all of you do, but just in case. pH is the phenyl ring. Benzyl is... Sorry, I made the assumption everyone knew what benzyl was, and that might not have been a safe assumption. Benzyl is when you have the extra CH2 in there as well. So what do we think about the relative stability of those? And so let's redraw this. I'm going to redraw this slightly. So I'm going to draw the resonance structures of both of these. Basically, I'm not hearing the answer I want yet, or the explanation I want yet, so I'm going to keep kind of poking until I find it. Are those two carbocations of equal stability?
No.
Yeah, they're different molecules, so the answer is no. Okay. So what's going to contribute to the stability of the carbocation?
The lone pair on the carbonyl.
So you're coming back to the Anchimeric assistance.
Mm-hmm.
Okay, let's not bring that in yet. Let's do it
Oh,
all
okay,
within
sorry.
this molecule. So before we start making new bonds or moving things around, everything just within this molecule. So not through, so that'll be sort of a through space interaction. I guess I want to talk about through bond interactions because that takes time. That thing needs to rotate to the right position. But there's stuff that kind of is happening instantaneously, or like at the speed of light, I guess, because electrons move at the speed of light. So that positively charged carbon, what does it do to the carbons next to it? Does it pull electrons from them, or does it donate electrons to them?
It pulls.
Yeah, right? Sweet, thank you. Okay, so we're pulling electrons. So if we're thinking about that, what we want is this carbon here to be as negative as possible or as not positive as possible. The same, two different sides of the same coin, right? If we want to stabilize that positive charge, ideally it would be a negative charge on that carbon, and we can make a double bond and it will be super and everybody will be happy. We can go home and we're done. It's not a negative charge because it's like saturated. It's got like hydrogens and shit on it. I didn't draw the hydrogen, but there's a hydrogen too, right? Like it's got 4 things on it. It's not a negative charge. Okay. So what affects the electron density on that carbon?
Would the oxygen affect?
Absolutely. Everything attached to everything, right? The everything is holistic. So of these 2 oxygens, now we're going to look at these guys. Which of those is more electron rich? And why?
The acetyl is, right?
Okay, where's its so in the acetyl, does that oxygen have full possession of its lone pairs in the acetyl? I guess what I'm saying is that the only way I can draw an acetyl group.
Oh, okay. No, because you donate into the carbonyl.
Right?
Yeah.
So there's a resonance structure for this. It's not a bad resonance structure. It's not a 0 contributor resonance structure. Like that.
I was thinking the other way around, but that's wrong.
Yeah, the other way around. Yeah, you're thinking the other way around. The other way around's wrong. This is right.
Yeah.
It's not possible. Have I lost anyone with that step? Ashley's been very quiet. I really want to thank Kirsten. Thank you for really fully interacting with this. This is better. Are you good? Is everyone good? Anyone have trouble following us right now? Okay. So now it should be staring us in the face. This guy here has all of his electrons. You know, he hasn't had to work with a surface that won't let him draw dots where he wants to draw dots. So the oxygen has the full set of its electrons to donate to this carbon to make it more negative so that it can donate more electrons back to this positive charge to make that less positive. This guy, though, doesn't have full possession of its electrons. It's slightly positive. And so he's not going to be able to donate as much. Donates less. So what this effectively means is that this is a more positive and this is a less positive because it's sort of mediated by the donation from the adjacent carbon to a greater degree. All else being equal, we want less charge, right? We want charge distributed. We want less charge concentration. We're actually going to get a 3-to-1 ratio of these guys on this reaction. And it all comes down to this idea. So what are we going to, so this concept's really important. I just didn't talk about this for this. Okay, well, partially because I find it interesting, but partially because it is important. And so in a general concept of chemistry being a male-dominated, violent, exploitative colonial exercise, we're going to continue with that trend. So we call this an armed donor. It's armed because it is electron rich and core electron rich. And we call this a disarmed donor. Because it's electron poor. And the armed donor is faster than the disarmed donor. And remember, if you can remember, we talked about donor and acceptor. And the donor is the thing that donates a glycosyl group. And so it's donating the glycosyl group because it's donating an oxocarbenium. And it's adding to the electrons of the nucleophile. And this is the exact opposite of how we think about things in every other bit of chemistry, where we think about electrons moving places. Here we're moving cations. And I'm sorry. I don't make up names. But this is called an armed donor, and this is a disarmed donor. And it's all about the electron richness of the system. And of course, it matters all the way around, but the closer you are to that oxocarbenium, the more important the effect. So differences at C2 are really important. Differences at C3, if the C2s were the same, differences at C3 would be less important. Distances at C4 would be less important. I don't think we could really detect differences at C6 because it's just so far away from everything. Okay. So this is what we need to, for this Anchimeric assistance thing, we have this Anchimeric assistance when we have an ester there, but it's slower because it's disarmed. And that's separate. Those are two separate concepts. Like the Anchimeric assistance is happening when we're going from B to C. And it allows us to stabilize C, so it gives us this preference to attack from the beta position. That's got nothing to do with how fast the reaction is. It's telling us why we're selective, but it has nothing to do with reaction speed. Reaction speed is about how fast can you do the rate determining step. And that's all about how stable is B. And B is more stable when you do not have Anchimeric assistance because you don't have this electron withdrawing group. And when you're doing Anchimeric assistance, you almost always have an electron withdrawing group. There are a few exceptions where you can do it with an electron donating kind of version of that. Okay. So what I want to think about now is solvent effects. So far we've done it with, let's go with an armed donor, but no Anchimeric assistance. We're not going to change everything else. Still got silver. Why not? we've got. So I am literally going to be pulling numbers out of my ass. Do the same, and ethanol. We'll have ethanol as a nucleophile. Why not? We'll stick with the same trend. I switch to ether as solvent. Ethanol as nucleophile. I switch to acetonitrile as solvent. This is not the official abbreviation for acetonitrile. I am going to use it because I use it. I'm just going to note that ACN equals acetonitrile. Because it looks like it's acetate nitrogen, but that's obviously not what acetonitrile is, because it's got this. And again, if you can't remember what acetonitrile is, it's that. So that's odd. Temperature's all the same. Promoter's all the same. Solvent is different. Different outcomes. So number one, this is basically pure anomeric effect. This is basically what we're seeing here is the anomeric effect. But what's happening with ether and acetonitrile? So in both cases, what's happening is happening through the oxocarbenium. So let's move on to the next slide. Draw an oxocarbenium. We could rewrite the problem basically as this. So again, let's think about this in terms of, and there's a benzyl group. I'm going to keep that in. Let's think about this in terms of the relative amounts of things present. You know, we're on the order of 10,000 to 1 of solvent to nucleophile. So mechanistically, I would draw this as, yay, ethanol comes in. I'm actually going to bring it in from the bottom because it's mostly alpha. And this is how, if I asked to draw the mechanism of this, you would draw, I hope. And you have to draw the full mechanism. You need to take off that proton. Another equivalent of ethanol would do that. You would hopefully draw something like that. And you'd be right, and you'd go home, and you'd get 100% on your question. Is that what's happening in the flask? Is it that simple, or is something else happening here too? So maybe a way for me to rephrase that question is, what do you think about the electron density on the ether oxygen versus the electron density on the ethanol oxygen?
I would say the ether has a greater electron density.
Yeah, it does.
Okay.
You're absolutely right. Do you know why?
Our ethyl groups are electron donating.
Perfect.
Yeah.
Absolutely, 100%. So what we've just drawn here doesn't make a lot of sense because I've just drawn the worst nucleophile attacking, and there's only one of them, and there's 10,000 of the other one, and the other one's a better nucleophile, and I didn't draw it attacking. So why did I draw ethanol attacking instead of ether attacking? It wasn't wrong to draw ethanol attacking, that's correct. But it's not actually what's happening. But why do we do that?
Is it because the ethanol can be deprotonated and whereas
Yep.
the ether can't?
Exactly. We only tend to draw productive reactions. This is something we always do whenever we do chemistry, whenever we draw a mechanism, we almost always only consider the productive reactions. And our brains are like, my brain is so well trained in this because I've been doing this for so long, but I think even you guys have been doing it long enough that your brains actually streamline yourselves a bit and you discount possibilities because you're like, yeah, you almost don't have to consider it anymore. It's just that's not really going to go anywhere, so I don't need to worry about it. So, you know, this, as Kirsten pointed out, is a more likely thing. This is more electron rich than ethanol. Assuming that there's no base in there that's able to partially deprotonate the ethanol and move electron density onto the oxygen off the oxygen hydrogen bond. Normally there isn't. Normally these are done under acidic conditions, so normally this is a very safe bet. And ethanol stands in for any alcohol, and most of what we're going to be doing here are alcohols. So, you know, it could be a really fancy ass sugar. Who cares? It's ethanol. It's all the same thing. So let's just think about this for a second. And the reason we don't really draw this is because this is all reversible. It doesn't get us anywhere. Right? You form it. There's nothing to be done except go back to the oxocarbenium. Except you know, this possibility of these SN2 like interactions instead of the SN1 like on the oxocarbenium. And then I could get into, and maybe we should, a discussion over how does this actually sit in ethanol or in ether? Does it sit as the oxocarbenium or does it sit as these ether substituted systems? And let's actually take a second and think about that. Which one do you think dominates? And let's say there is no continuum. We're going to talk about dichotomies, very traditional. It is either the oxocarbenium or it's the ether substituted version. Which of those positive charges is more stable? And pick either the alpha or the beta, it doesn't matter. Let's whatever. Electronically they're identical. Do you prefer that positive charge or that positive charge?
Is it the one with the double bond because there's less atoms involved? I think.
I don't quite follow the less atoms involved.
Like across the 3 oxygen, like the ether has like 3 carbons attached to the oxygen, whereas the oxocarbenium only has 2.
Okay. I'm not sure I completely, but more carbons attached to the oxygen would be more electron donating to the oxygen.
Okay.
So I agree that it's the oxocarbenium. I don't agree with your reason. Because on your reason, having 3 carbons donating electron density into this positive charge would be better than only having 2.
Right.
3 is better
That
than
makes
2.
sense.
But what else is going? What is the other difference between where that? Again, but you're getting at the core of the issue, which is you're talking about delocalizing positive charge. So is there another way we're delocalizing positive charge in one of these forms?
Is it that you can break the double bond and form a carbocation? Or
Perfect.
is
You
it,
have resonance, right?
yeah.
So you have a resonance structure, so you can formally put the positive charge on that carbon. There's a lot more electron migration there. So you're sharing that positive charge between the oxygen and the carbon, whereas here you don't have any possibilities for resonance. That positive charge is going to be partially mediated by the multiple carbons surrounded by induction, but it's minor compared to the resonance stabilization. So this is more stable. Okay. But we're really kind of in this fluxional space between all of them. And what we're probably having is, partial bond formation at all times. The ether's kind of making sort of a bond, stabilizing it. We're kind of sharing it, and because again, we can share over more things. And what I mean by that is the most common thing that we're probably no, bad John, don't draw as a chair. Boat. The most common thing we're probably having is something like this: delta plus, delta plus, delta plus. Everybody's kind of sharing the charge. Okay. So, if this is the most common thing we're having, we've got 2 different options for it. Again, alpha and kind of beta kind of thing. So which of those is more stable? The charges are all the same. We were talking about charge earlier. So the electronics are all the same now. So let's go back to the very beginning of this lecture. We were talking about the reverse anomeric effect.
The beta would be favored because you have a positive charge on the oxygen.
Right. And so because you have partial charge, you're going to have other ether molecules trying to help out. Somebody else making bread?
No, that's my timer for the HPLC.
Oh, okay. I was making bread today and my timers were going off. So we have the same issue we have with the reverse anomeric effect. This is more crowded. So this is more stable than alpha. So we prefer having our ether beta because that reverse anomeric effect thing. I'm going to call it the reverse anomeric effect, even though it's not really a thing. It's more just that there's a, well, it is a thing, but it's nothing to do with the anomeric effect. It's just, it's the steric requirements of a positive charge at the anomeric center don't want to be axial effect. But that is just way too much of a mouthful, so I'm going to stick with calling it the reverse anomeric effect, even though it's not a thing. So this beta is more stable. So let's think about that. So even if we don't have a formal charge there, our ether is going to be sitting kind of at this beta position. And so that opens up the possibility for our nucleophile to come in, and that's going to come in alpha more selectively, because now we're kind of blocking the beta phase. We were already, all else being equal, we were using dichloromethane, which just floats around, doesn't do anything, just, minds its own freaking business. We already were favoring alpha. But now we're favoring alpha even more because we have this extra steric thing, because the ether is going to sit at the beta position, because it's going to be less hindered when it's positively charged there. And because it can interact with that, it's going to help stabilize that positive charge. Because although the oxocarbenium is better than either of these, this kind of mixed form here, or the ability to kind of switch back and forth between these, is better than being stuck with the oxocarbenium alone. Things always like being able to, flip back and forth between other stuff. So let's just write that in something reasonable instead of me drawing arrows and lines and circles around everything. Because sterics of other solvent molecules. Therefore, attack tends to be alpha. Okay. So going back to that table a few slides back, here, ether blocks beta is a way of thinking about it. Okay. Great. Acetonitrile is doing the opposite. What's going on there? You know what? It's 5:10. I'm yawning all the way through class today. How will we take up acetonitrile next class? I think that makes sense. Yeah, but maybe before we leave, does anyone... This is confusing. And it's challenging. I think it deserves probably going back over your notes a few times. I think this is really, really important, because we're talking about the subtleties about how sterics and electronics play in together. And we're considering the fact that reactions are not occurring in vacuums, but they occur in solvent. And solvent participates in reactions. And that's really, 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 really important. I probably didn't have enough reallys in there. So, any questions about that? Okay. So we're going to refer to this kind of thing as the ether effect. And there are other solvents other than ether that do that. Basically, anything that has, some steric bulk and an atom with a lone pair can do this. Like nitrogen-based molecules, oxygen-based molecules, sulfur-based molecules can do this kind of similar interacting at the beta position. You see this in sugars, you see this in natural product chemistry, you see this all over the place. and it's a way you can sort of tune your reaction. So I guess we will take up acetonitrile starting this class. Have a really good. So I'm gonna put a couple of papers when I find them into the onto Blackboard about the reverse Anchimeric effect and debates that were going on about that, and we'll take it from there. Okay.
Great. Thank you.
So
Thanks, John.
Okay, bye.
Bye.
Bye, everyone.